Some compounds are classified as acids and bases, and they are done so based on a couple of different definitions of how they behave in a solution. But in general, compounds that are acidic in nature are common in that they all tend to have a sour taste, and they are corrosive when they react with metals or other substances. They tend to wear away at it by chemical action. Different indicator types react differently to acids. One common type is litmus paper, which is just a strip of paper that is treated with a chemical, and there's blue litmus paper and red litmus paper. Acids won't react to red litmus paper, it'll just look like wet red paper, but blue litmus paper will actually turn a bright red color. Bases, comparatively, will have a bitter taste to them. If you've ever gotten soap in your mouth, you know the sort of bitter taste associated with bases. They are, when you get a base on your hand, it also feels kind of soapy, but it's not soap. What it's actually doing is denaturing the proteins in your skin and destroying them, and so the slipperiness you feel is those destroyed protein molecules sliding past one another. Bases are considered caustic, which means that they will wear away at organic tissue and eat away at biological material. So in some ways they can actually be more dangerous than acids. Alright, and in terms of litmus paper, red litmus paper will turn blue, while blue litmus paper will do nothing in the presence of a base. Now there are different ways to define what is an acid and what is a base, and even though there are a variety of different definitions, what would be classified as an acid in one definition would be an acid by all the definitions. The most common one is known as the Arrhenius theory. And the Arrhenius theory is based on the fact that acids and bases are substances that when they are dissolved in water will be able to conduct electricity. Those solutions will be able to conduct electricity. Now Arrhenius in his studies noted that these acid-base solutions were able to conduct electricity, and concluded that when the acid or the base was dissolved in the water, it released particles that were capable of transmitting the electrical current or carrying that current. These charged particles we know as ions. Now according to the Arrhenius theory, when an acid is dissolved in water, and we know that acid formulas typically start with hydrogen in them, that's the ion that will be produced. Acids produce a hydrogen ion, which is really just a free proton. When that binds with water, because a hydrogen ion, a proton by itself, is very unstable, when it binds to water, it actually forms the hydronium ion, H3O+. And realistically, this is how the hydrogen ion truly exists in solution, but oftentimes we'll just see H+ written in equation form. Arrhenius bases, on the other hand, are substances that will produce hydroxide ions when dissolved in solution. And so they are readily recognizable anytime you have a hydroxide compound that is aqueous, which is not all that many, because most hydroxides are insoluble in water, but aqueous hydroxides will be basic in nature. By the early 20th century, it became necessary to come up with an alternate definition of acids and bases, because it was found that there were compounds that had all the properties of a base, behaved similarly to bases chemically, but they didn't contain hydroxide ions. And so in the early 20th century, a Danish chemist and an English chemist working independent from one another, Brønsted-Lowry, proposed that when you have a chemical reaction, anytime a substance donates a proton to solution, that substance is going to behave as an acid. And that's exactly the same as what Arrhenius had said about acids. It donates a hydrogen ion or a proton. The difference is that a Brønsted-Lowry base is a substance that will accept a proton, so there is no need for it to have hydroxide, and substances like ammonia and H3, which have a lone pair of electrons, that is a site that would be able to accept an incoming free proton. Now when an acidic substance gives up its proton, the particle that remains is now basic. And conversely, the base, when it accepts a proton, in the reverse reaction would now have the proton to donate, so it becomes acidic. So if we take a look at the first reaction here, we have NH3 plus H2O yielding ammonium plus hydroxide. Now if we compare left side to right side, the species that is donating a proton is the water. Starts out as H2O, and then on the product side we see that OH has lost one of those hydrogens. So the water is acting acidically. The ammonia is picking up a hydrogen from the left to the right, so it's accepting a proton, therefore it's the base. Now, the corresponding species on the product side are your conjugates, but your conjugates are reversed from what the original species was. So for instance, your ammonia was a base to start with, but once it's picked up the proton, now it has that additional proton, so it forms the conjugate acid. It's the acidic particle on the product side. And the conjugate, the corresponding species for water that has lost its proton, the hydroxide, is known as your conjugate base. In looking at the second reaction, you have acetic acid plus a cyanide ion yielding hydrogen cyanide and the acetate ion. Obviously the acetic acid is going to be the acid substance, whereas the cyanide ion is going to be the basic substance. Your conjugates then, once the cyanide ion has picked up the hydrogen, you have hydrogen cyanide or hydrocyanic acid, which would be your conjugate acid, and the acetate ion makes up the conjugate base.